Well, Mona, if you permit me, should I leave the session?
Yes, but also I'm going to leave because now is Professor Nizar, the chair of the session.
Okay. So
Okay.
So we should leave. Thank you very much. Okay.
Thank you. Yes.
Okay. Bye bye. Take care.
Sure.
I think.
Excuse me. This is Alma again. Sorry for interrupting you.
Everybody see my presentation?
You are going to do your presentation first?
This is what I have informed for the ISTS office just now.
It was not possible. I lost the internet in the place where I am now. And you can go on. And when you finish, maybe I'm going to be online again. Okay?
No problem.
No problem. Okay, thank you very much. I can go on after you, but because now I am connected with my iPhone, not with my laptop. I'm not sure I can make the presentation through iPhone, but let me try. You can go on with your presentation. After you, I'm going to retry. Thank you very much, and I'm sorry apologize for this inconvenience.
No problem, no problem. So everybody understand my sound or hear me very well? My screen is appearing to everybody now? So I can start. I want to start. So I'm Nizar Assi from Department of Civil Engineering at Birzeit University from Palestine. I'm going to present my work entitled Numerical Investigation of Performance of Continuous Composite Girders with Ultra-High Performance Concrete Slab at Hogging Moment region. We have a lot of applications in real life where we use composite concrete steel girders. One of these applications that we see in our life is the bridge, where we have steel beams that support concrete slabs. The most important thing in composite construction is that the composite construction mainly depends on the composite action between the concrete slab and steel beam. And this composite action forms by providing shear connection, adequate shear connection between the steel beam and the concrete slab. If we don't provide any shear connection between the steel and the concrete slab, then there will be huge slip between the two sections and there is no interaction between them. A slip will take place at the interface between the slab and the steel beam. With a partial connection, then a partial interaction between the two materials will take place. Small slip will happen at the interface between the two materials. With a full degree of shear connection, we'll have a full composite action, complete interaction between the two materials. However, in continuous composite girders, this composite action may be lost due to the tensile stresses generated in the concrete slab. Different researchers have tried different construction schemes to maintain the composite action at the Hogging moment zone for continuous composite girders, like internal and external pre-stressing techniques, carbon fiber reinforced polymer, CFRP sheets bonded to the top of the concrete slab at the Hogging moment zone, and steel fiber reinforced concrete at the Hogging moment zone. And I did an experimental study to investigate the behavior of these girders retrofitted or strengthened using ultra-high performance concrete. The findings of these studies are the composite action and the negative moment was maintained for the service load level. The development of cracks were prevented at the service loads. We increased the service load level. An enhancement was obtained for the stiffness of the girder and the load carrying capacity, and the mid-span deflection was reduced as well. The current research is to develop a three-dimensional finite element model for the continuous composite girder with Uhpc slab at Hogging moment zone using commercial software, ABAQUS software, which is a nonlinear finite elements software. This model will be developed for the composite girders with the ultra-high performance concrete slab at the Hogging moment region and will be validated with the experimental results as we've done previously. This model, the validated model, will be employed to conduct a parametric study to evaluate extra parameters, extra variables of the Uhpc slab, the effect of the Uhpc slab length. I consider only one variable, the effect of the Uhpc slab length at the Hogging moment zone on the behavior of continuous composite girders. The previous experimental work was for this continuous beam, where we have two-span continuous beam, composite beam, steel and concrete beam. The detailed sections and the longitudinal profile of the beam are shown in this slide. Here, as shown, the ultra-high performance concrete was cast at the negative moment region, which has a length of 1300 millimeters. The load is applied at the mid of each span, 2-point loads, one on the left span and the other on the right span. The experimental work conducted previously was considered only two variables: the spacing between the shear connectors at the negative moment region, which means the degree of shear connection between the concrete slab and the steel beam, and the thickness of the Uhpc slab used at the Hogging moment region. So 4 girders were cast and tested experimentally to consider these two variables. But that experimental work did not consider the effect of the length of this Uhpc slab at the Hogging moment zone. The schematic and the actual test setup is shown in this figure. We apply the load at the mid of each span, we apply the point force at the mid of each span as shown in the figure, and the load was a static load. Now I will talk about the content of the current study. Finite element modeling of the continuous composite girders with Uhpc slab at Hogging moment zone. Different models were developed using ABAQUS software, which is a finite element based software, to conduct this numerical study. 4 models, which are identical models for the experimental study and called G1 up to G4. These 4 models were developed for the sake of validation and calibration of the model. And another 6 models were developed for conducting the parametric study to evaluate the effect of the length of Uhpc slab on the performance of continuous composite girder. First of all, let's talk about the geometry and the mesh modeling. Different elements were incorporated in this finite element modeling for the steel beam and the steel stiffeners and the steel plates over the supports and the shear studs and the concrete slabs. A 3D stress 8-noded linear track element was used to model these parts. While for the steel reinforcement, 2 nonlinear 3D stress element was used. The geometry of the developed 3D finite element model and the overview of the mesh model are shown in the slides. In this slide. Mesh sensitivity analysis was conducted to reach the proper size of meshing that will not affect the behavior or the results of this study. The load was applied at the mid of each span. As you see, we used a rigid steel plate to distribute the load in order to overcome or to prevent any stress concentration within the concrete slab. For the interaction between different materials and different bonds in a model, we have different contact as shown in this table. Tied or perfect interaction, perfect bond was used to model the connection between the stiffeners and the steel beam, bearing plates and the concrete beam, shear studs or shear connectors and the steel beam. While normal and shear fraction was used to model the connection and the interaction between the concrete slab and the steel beam and the layers of the normal concrete and ultra high performance concrete and the shear studs and the concrete slab. The reinforcement, steel reinforcement within the concrete slab were modeled as embedded elements inside the concrete slab. For the material modeling, normal concrete and ultra high performance concrete was modeled using concrete damaged plasticity model. For the elastic properties within the elastic range, this table shows Young's modulus Poisson's ratio. As you see here, that Young's modulus for ultra high performance concrete is double of that for the normal concrete. So we expect that the behavior of the girders strengthened using this type of concrete will have higher stiffness within the elastic range. And this will be observed during discussing the results. Material nonlinearity was considered in the model. So stress strain diagram for concrete materials in tension and compression was modeled in ABAQUS software. For the steel materials, we have here two types of steel: the structural steel section, the I section, and the reinforcement steel. Isotropic plasticity model was used to model these two materials. The mechanical properties of the steel materials within the elastic range, including Poisson's ratio and Young's modulus, are summarized in this table. The stress and elastic strain for both materials are considered in this model, where we have strain hardening as well. Strain hardening was considered. Now I will talk about the validation of the finite element. So the validation was made through different stages. First stage, using the load deflection curves, which were obtained experimentally. As you see for the G1 and G2, and here we have load displacement curves for the other two girders with different shear connections and different thickness for the Uhpc slab. The comparison shows good agreement between the finite element model and the experimental results in terms of load deflection curves. In addition, validation was conducted using cracking, yielding, and ultimate loads. This table summarizes the values of the cracking, yielding, and ultimate loads obtained experimentally and using finite element software. The percentage difference between the experiment and the finite element is less than 5%. Here we conclude that the developed model is very accurate in terms of these loads. The model was capable of detecting the cracks developed within the concrete slab in the hogging moment region. As you see in the left figure, in the red region here, these are the cracks obtained using finite element analysis. And on the right, these are the cracks developed in the UHPC slab obtained experimentally. The model also detects the mode of failure, the shear compression mode of failure, which took place at the mid span in the concrete, shear compression failure within the concrete at the mid span. So on both spans, because we have symmetry in the speed. So we can conclude that this model is validated and it can be used to predict the effect of new parameters which were not tested experimentally. Therefore, we decided here to extend this experimental work numerically and investigate the effect of the length of the UHPC slab and to see what is the probable length that achieve the desired performance of the UHPC slab. From the experimental study, we concluded that half depth UHPC slab thickness and 50% degree of shear connection are sufficient to achieve the desired performance of the continuous composite girders. Therefore, I will continue with the numerical analysis using 50% of full shear connection and 45mm thickness UHPC slab. The only variable I will show now is the length of the UHPC slab, is this length. So I tried numerically to model the continuous beam considering different lengths. First one with no UHPC, which is the control specimen. Second one with a 300mm length up to 1500mm UHPC slab length. And then we'll see the results now. Now for the load mid-span deflection. As you see, the red curve, which represents the load displacement curve for the girder with no UHPC slab, we have very low stiffness compared to the green girder, which was constructed using UHPC slab with a length of 1500mm. So within the elastic range during this early stage of loading here, as increasing the length of the UHPC slab, the stiffness of the beam will increase significantly. But during the ultimate stage here, there is no significant enhancement in the behavior of the composite girder with different lengths. So we can conclude that the length of the UHPC slab enhances the performance of the girders during the service life of the girders, not during the ultimate or failure conditions. In terms of cracking load and yielding load, as increasing the length, the cracking load will increases as well. As increases the length of the UHPC slab, the cracking load and the yielding load increases. But for the small length, from 0 up to 600mm UHPC length, as you see, the cracks developed within the normal concrete, not within the UHPC. But with a length higher than 900mm, the cracks developed within the UHPC slab, and the cracking load increased significantly. For the yielding load, yielding of steel starts at the bottom flange at the midspan section, and the value of the yielding load increases significantly with the increase in the length of Uhpc slab. If we define a parameter lambda, which is the ratio between cracking to yielding load, we'll see that the value of lambda is less than 1 for the length from 0 to 600 millimeter, and is higher than 1 for lengths from 900 millimeter to 1500 millimeter. Cracking load is the lower limit for the service life, and the yielding load, we can define it as the upper limit for the service life of the girder. So when we reach a lambda equal to 1, so we increase the lower limit of the service life up to the upper limit. The service life of the girder increases with this 900 and 1200 up to 1500 millimeter slab length. The conclusions that can be drawn from this study, that the performance of girders was improved significantly in terms of the stiffness, cracking load, yielding load, and lambda values. The continuous girder with Uhpc length of 900 millimeter gave a lambda value close to 1, which represents a satisfactory length necessary to maintain the composite action at the Hogging moment zone. Therefore, it can be concluded that the length of Uhpc slab at Hogging moment zone can be taken as 20% of the span length to achieve the desired performance of the continuous composite girder. And thank you for your listening.